Hi, my name is Sophia Bradach, and today I would like to speak to you a little bit about my research on the effects of nitrogen fixation in Medicago Sativa, which is just alfalfa, in microgravity. So I'd like to begin by explaining what nitrogen fixation is, what that process is. So it is a symbiotic relationship between bacteria called rhizobium and legumes, wherein this bacteria infect the root hairs of the plant using an enzyme called cellulase and form nodules. And then once the legume gives the rhizobium a signal that they need more nitrogen, these bacteria who are receiving things like sugar from the legume will use nitrogenase to bind atmospheric nitrogen into components that the plant can use. And this is incredibly important because it will often leave residual nitrogen that wasn't there before back into the soil. This is often used in plant rotation, crop rotation on farms. So if you have a particularly nitrogen draining plant, the season before, the next season you'll plant a legume. So you get some of that nitrogen components back in the soil. And for spaceflight, this is equally as important because in order to make spaceflight or long-term spaceflight a reality, we would need to make spaceflight self-sustaining and sustainable. If we ever want to go to places like Mars, we'd have to develop that soil into something that we could use. And processes like nitrogen fixation are incredibly important to that because of its ability to add components into the soil while also providing nutrition for human beings and developing sustainable subsistence agriculture in space. So I'd like to talk a little bit how we researched the effects of nitrogen fixation in Medicago Sativa in microgravity. So we had this silicone tube. It was divided into 3 sections, blocked by 2 clamps, clamp A and clamp B. You can see that in the center right there. In the first section, it had the vermiculite, which is a synthetic soil that was autoclaved to avoid any other bacteria entering our system. We had our alfalfa seeds, and we had the rhizobium bacteria. Then we had the clamp there, and we had 2 milliliters of water in the second chamber. Once that clamp is removed, which is removed once it got to the International Space Station, the water entered the system, and on the same day we did that down here, which allowed germination to occur and which started our experiment. And the last chamber contains neutralized buffered formalin. And once that clamp is released, it ends the experiment. It preserves everything inside, but also stops everything. So that way, once it came back, we had no excess growth. And we analyzed this. Coming back, we took some pictures and measurements using a camera attachment on our microscopes. And we did see some notable differences in growth and development as well as nodulation in these alfalfa plants. So the ones that went to space were less likely to form nodules, and the nodules that they did form looked a little bit different. If you look down here, you can see they're more condensed and there's less of them as compared to the ones that were growing down in standard gravity. And growth and development are going to be a little bit different in space. A lot of plants go hypoxic or grow upside down because they can't tell where down is, and that is confusing for a plant. But we did see a significant difference in sprout length and width, as you can see in this chart right here in blue for sprout development. And you can even see the differences in leaf development. There tended to be a little bit smaller and less leaves on each alfalfa sprout. In the future, I plan on analyzing the root systems, using some cytology, sending it through a series of alcohols and then paraffin waxes, and then sending it through a microphone, slicing it really thin, and looking at those cross sections. I really hope that notification didn't show up. And looking at those cross sections with some stains that are well, highlight rhizobium bacteria well, so we can see the differences in the formation of those nodules. And overall, I think that we were able to identify some significant differences, and I'm hoping that in the future, as we continue, we'll be able to more clearly see what those differences are. And potentially, if this were to be built upon, maybe allowing light into the experiment, because our experiment only allowed light in our ground experiment. Maybe this could be crucial in developing systems for foreign soil development, like if you wanted to do something on Mars, or sustainable subsistence agriculture in space. Thank my advisor, Dr. Peter Straub, and the New Jersey Space Grant Consortium for allowing me the opportunity to conduct this research, as well as the Student Space Slice Experiments Program and the National Center of Earth and Space Science Education.